NASA 747, like to start engines on NASA rim.
NASA 747 Heavy engine start, approved. Thanks for the heads up. NASA 747 Heavy, Palmdale ground, runway 25, taxi via Sierra, Echo Papa. Hold short, runway 22 at Sierra.
Hold 22 Sierra, NASA 747.
NASA 747 Heavy on departure, turn right heading 070, climb and maintain 7,000.
7,000 on departure on NASA 747.
NASA 747 Heavy, runway 25, wind 220 at 10, clear for takeoff.
On 25, NASA 747, and we'll be in position for about another minute. NASA 747's on the roll.
Roger.
Dusk falls on Southern California. Just as it happens every evening all over the world, the first stars become visible in the night sky. To us, they appear as sparkling white dots in the sky. Some of them shine brighter, others are fainter. Ancient cultures believed that stars were tiny holes in the crystal sphere of our sky, through which cosmic light reached us. As it slowly grows darker, more and more stars appear. These sparkling points of light look like little diamonds in a deep blue treasure box. Thousands of them are visible with the naked eye. How many more lurk in the depths of the universe? Where do the stars come from? Where are they born? How do they evolve? And how do they die? We are astonished at their seemingly infinite numbers, their different brightnesses, even their colors. And we are in the midst of this starry dance ourselves. All stars visible from Earth are part of the Milky Way galaxy. Its shimmering band spans over our night sky. The Milky Way with its 200 billion stars. This is our galaxy, our cosmic home. Even with simple telescopes, we discover numerous nebulae in this fuzzy band. Photographs reveal their magnificent shapes and colors. We see shimmering clouds of hydrogen, the basic element of stars. We see how this hydrogen is compressed in some places. Where interstellar gas and dust accumulate, dark columns rise up as silhouettes against the backdrop of the nebula. We know today that the creation of young stars takes place in the interior of these dark clouds. Our Sun, the planets of our solar system, and even our Earth were formed in such a place. But the most exciting parts remain hidden to us. The light that young stars radiate into the cosmos is immediately absorbed by the dust clouds. How can we peer into these stellar nurseries? Can we watch as young stars are forming?
The 20-meter tall gates of NASA Building 703 opened to give us a first glimpse into a gigantic hangar. With the size of 4 football fields, there is enough space for half a dozen aircraft, one of which is a converted Boeing 747 SP. In its former life, this plane regularly carried passengers from Los Angeles to Australia and Asia. Today, it serves science. Technicians and scientists are busy getting the plane prepared for its nightly mission. The fuselage of a Boeing 747 SP is much shorter than that of a normal jumbo jet. This gives it its characteristic appearance. This reduction in weight enables the aircraft to have a longer flight range and, more importantly, reach higher altitudes. Thus the abbreviation SP. It stands for Special Performance. Behind the wings, there is a large door in the fuselage, more than 12 feet wide. This door protects a highly sensitive telescope with a weight of more than 17 tons and a primary mirror with a diameter of nearly 9 feet. This plane is a flying observatory, the Stratospheric Observatory for Infrared Astronomy, SOFIA. SOFIA is a joint project of NASA and the German Aerospace Center. The SOFIA Institute in Stuttgart manages the German part of the project, while NASA Ames Research Center in Mountain View, California, and NASA Armstrong Research Center in Palmdale, California, are responsible in the United States. SOFIA differs from other aircraft in many ways. Passenger seats have been replaced by computer terminals and workstations. While in the case of a passenger aircraft, everything is done for the comfort of the passengers. On this plane, technicians are busy working on the cooling of the highly sensitive scientific instruments. As coolant, they use liquid helium with a temperature of minus 450 degrees Fahrenheit. The crew meets about 2 hours before takeoff. Pilots, technicians, and scientists review their mission plan. The flight plan and weather forecasts are also checked one final time. A few hours before takeoff, SOFIA is pushed out of the hangar.
Stars send out their light from the depths of the universe. With the naked eye, we can spot the band of the Milky Way in the middle of a dark ocean. However, much of the radiation from the universe we cannot see. Satellites with special cameras make it visible to us. X-ray satellites show us particularly hot areas of our Milky Way. We see that our galaxy is surrounded by hot gas. Very cold areas of the Milky Way, on the other hand, are visible in the range of microwave radiation. We see how hydrogen, the building block of all stars, pervades the universe. This hydrogen is visible in microwaves because it is much too cold to emit visible light. Cameras that show us the universe in infrared light are capable of looking through interstellar nebulae. They show us the birthplaces of young stars. The Earth's atmosphere protects us from most of this cosmic radiation. Neither X-rays nor microwave radiation reach the surface of the Earth. Only radio waves and the light visible to our eyes can freely pass through Earth's atmosphere. Infrared radiation only penetrates the atmosphere down to an altitude of 8 or 9 miles above the ground, where it is absorbed by the water vapor in the lower layers of the atmosphere. Due to this absorption, telescopes on the surface of the Earth are not able to see what is happening in the universe in infrared light. So for decades, astronomers had to rely on satellites outside Earth's atmosphere to gain new insight from the depths of space. Infrared cameras, however, must be cooled with liquid helium, as their own heat radiation would otherwise ruin astronomical images. But this helium is consumed very quickly, and the satellites must cease operation after only a short period of time. In contrast, an infrared telescope installed in a special aircraft can be refilled with fresh coolant and can be equipped with the latest instruments. At a cruising altitude of 8 to 9 miles, more than 95% of the total atmospheric water vapor is below the aircraft, and thus below the telescope. These are ideal conditions for astronomical measurements. We are in the stratosphere. Here the air is 5 times thinner than at sea level. Ordinary airplanes do not venture to such heights. Numerous tests in a wind tunnel were necessary to make sure that SOFIA still generates sufficient buoyancy and ensures a safe and stable flight, even with the open door. After takeoff, the materials used to construct the sensitive telescope must withstand a temperature drop of up to 200 degrees Fahrenheit without deforming.
Even at this altitude, there is turbulence. The slightest vibrations, air turbulences, or course corrections would disturb the high-precision instruments to such an extent that the images would become unusable. For the scientists, this would cause a loss of valuable observation time, in addition to delays after months of preparing and waiting for flight opportunities. Therefore, Complex mechanics and electronics keep the telescope stable and perfectly aligned with the astronomical object under observation. The telescope thus performs an impressive dance during an observation. This can be best observed from the cabin. The instruments and cameras are located behind the pressure bulkhead, but are firmly connected to the telescope on the other side. Every movement of the telescope, every tiny vibration is visible from this side. It looks as if the telescope is shaking and wobbling, but in fact the telescope stands still. It is the plane that is moving relative to the telescope. For this piece of art to be successful, years of research and many thousands of hours of engineering had to be invested. The telescope was developed and built in Germany, with NASA being responsible for the aircraft. The German project participants are responsible for maintaining and operating the telescope, whereas NASA runs the plane and ground operations. Both German and U.S. scientists and technicians are on board during the flights to monitor and control the observatory. During a 10-hour observing flight, many things can go wrong. Any problems that occur must be solved immediately, as every minute of observation time is precious. Thus, the atmosphere on board is focused, even tense. Each nightly flight has been precisely planned for months in advance.
The telescope points towards port of the aircraft's fuselage, in other words, to its left. If the SOFIA crew wants to examine a certain star in the sky, the plane has to fly at a right angle to that star. Due to the rotation of the Earth and the movement of the airplane itself, the direction of observation is always shifting. Therefore, the SOFIA crew must continuously adjust its course in order to keep the star in the telescope's field of view. Thus, SOFIA doesn't fly in a straight line, but always in a slight arc. As soon as a new object is selected, SOFIA adjusts its flight direction accordingly. Usually, several different observations are carried out this way on any given night. The most important part of mission planning is the development of a balanced flight plan. The airplane needs to return to Palmdale at the end of the 10-hour flight without losing expensive observation time. The mission director is responsible for the supervision and correct implementation of this flight plan and remains in contact with everyone on board via radio telephone. The director is informed about the status of the telescope at all times, gives course corrections to the pilots, and arranges things with the technicians on board. In addition to the mission director and deputy, the crew of SOFIA consists of 2 pilots and 1 flight engineer in the cockpit, 2 safety technicians who are trained for special emergencies, 3 operators responsible for correct alignment and trouble-free operation of the telescope, and 3 technicians who are responsible for the camera and measuring instruments. They are in permanent contact with the accompanying scientists who are already carrying out initial evaluations of the data on board. Here we see another advantage of SOFIA: discussions among the technicians concurrent to or immediately after the measurements. This allows measurements to be optimized and improved on the spot. Thus, the valuable observation time can be used in the most efficient way. On many research flights, the crew is supplemented by guests. At times, there are teachers, journalists, or even politicians on board. At special computer terminals, they can track the flight and experience in real time, as cosmic gas clouds, alien planets, black holes, or distant galaxies are being explored. Other technicians and specialists are on board SOFIA on particularly demanding or critical missions, such as the night of June 30th, 2015.
That night, the dwarf planet Pluto pushed itself in front of a star in the constellation of Sagittarius. However, this occultation was only visible from Earth within a very small area in the southern Pacific Ocean, and only for a few seconds. Observing this occultation with SOFIA, scientists had the opportunity to determine whether Pluto has an atmosphere and maybe even learn about its basic composition. But the mission could only be successful if SOFIA was in the right place at the right time. Even during the flight, calculations were carried out and course corrections were made. The excitement among the scientists involved was intense, as this observation cannot be achieved with any other telescope. Everything depended on the calculations being correct and the technology on board SOFIA working well. And so it happened that Pluto's shadow fell on the telescope and was captured by its instruments. From these observations, scientists were able to conclude that Pluto had an atmosphere and even clouds. Sometime later, this was impressively confirmed by the flyby of the New Horizons spacecraft. It was the data from SOFIA that contributed significantly to the preparation of these spectacular images. SOFIA's measuring instruments, in contrast, mainly generate long and complex series of numbers, curves, and diagrams. Special computer programs with sophisticated algorithms then generate images from this data. In a direct comparison with images from conventional optical telescopes, they seem inconspicuous at first, but they reveal things that would otherwise remain hidden. SOFIA's instruments are able to measure cosmic magnetic fields and make them visible to us. We are just beginning to understand how these magnetic fields influence the structure of the universe, how they affect nebulae and star formation. Here, SOFIA opens up a new window for us, a new view to the cosmos that had previously been hidden from us. We live in a gigantic universe, in a fantastic universe. It still holds many mysteries. But thanks to SOFIA, we understand the universe around us a bit better. Interstellar clouds of gas and dust shroud the birthplaces of the stars. In visible light, we cannot see much more than a curtain of mysterious dark structures. But SOFIA observes the universe in the infrared range of the electromagnetic spectrum. This radiation passes through clouds of gas and dust. It provides us with information from the unknown regions of the universe. And now we can see what remained hidden for a long time. Thanks to SOFIA, we are witnessing a process that is so important to us: the birth of new stars and planets.
we see clouds of hydrogen with a diameter of several light years. Under the force of their own gravity, they collapse, starting slowly, then faster and faster. This collapse creates heat, but far too little for the clouds to shine in visible light. But in the range of microwave and infrared radiation, these clouds appear as bright structures. As gas and dust continue to collapse, the cloud begins to rotate and flatten. A protoplanetary disk is evolving. This is the fetus of a young planetary system. Invisible forces are at work here. Gravity is compressing the gas. The rotation of the disk counteracts the collapse. But everything is still fragile. Even a slight disturbance is enough to destroy what formed over millions of years. An encounter with a nearby star or another protoplanetary disk would destroy it all. Magnetic fields penetrate the disk. The instruments on board of SOFIA are able to make these fields visible. According to current astrophysical models, many small stars, but no large stars, develop in these gas clouds. Is it the magnetic fields that enable the formation of more massive stars? When the protoplanetary disk continues to compress, the pressure and temperature in its center eventually reach a critical value. Under these extreme conditions, hydrogen begins to fuse into helium. This releases unimaginable amounts of energy. A new star is born, orbited by the remains of its creation.
We witness the birth of giant stars. Due to the extreme temperature, they glow bluish. They fuse their hydrogen so quickly that they disappear again after only a few million years. Life would hardly have time to develop on a planet around such a star. With SOFIA, we have observed how the extreme radiation of these giant stars disturbs and prevents the formation of other stars and planets in their surroundings.
We observe the formation of small red dwarf stars, which glow over many billions of years. Their radiation is so weak that it scarcely gives any warmth to a planet at all. In many disks, binary star systems form. Can planets like our Earth also be created here?
A young sun shines in a disk of gas, dust, and rock. The star's radiation pushes almost everything out of the innermost areas of the disk. A few million years later, gaps appear in the areas further out. Gas giants are blazing their trails. Only far from the star can light gases accumulate to form these massive planets. Somewhere out there, water must have accrued. Closer to the star, radiation would be too strong for that. Only heavier elements such as iron, silicon, or carbon were able to remain in the inner and seemingly empty areas around the star. Slowly but steadily, smaller rocky planets emerged there. Impacts of comets from the outer parts of the system bring water to these inner planets. One of these planets has ideal temperatures so that water can exist in liquid form.
A great number of bright stars shine in its sky. Over hundreds of millions of years, they diverge. They form a star cluster, which is getting larger and larger until eventually the stars go their own ways. Is this our own history?